So we get one bound for the sum weight. Now we're trying to construct another bound. This is a tricky one that is a pretty careful one. It's introduce a so-called mu sum bound. Basically, we are trying to construct something like that's the mu sum. So-called mu sum is something like that. We have a y here is equal to just a linear combination of the x1 and x2. Now at the decoder, we're trying to reconstruct not just x but also y now, and just let's see, and we can compute okay, here I'm just trying to compute the covariance matrices for like x hat and y and so on. Let's see why I need that. I probably need that later on. And for the mu sum bound, now if I consider the mu sum bound, now I do the more or less similar things as before, but this time we also insert this, like we have hm1 m2, the nr1 plus r2, the sum weight times n is bigger than hm1 m2, is bigger than the mutual information, but we also add this yn here. And then this we split in another way and have this and so on and so forth. So now, then afterward, we kind of split into 3 terms now. So now we have 3 different terms here, and we need to compute each of this term for the mu sum bound. And so for the first one, so we have hxiyi, then basically this will be just equal to 1/2 log 2 pi e, okay, or like 2 pi e times the covariance of this that thing, right? Actually, essentially, I have it here. So let's compute that. Compute this covariance matrix, and it is equal to actually determinant of the covariance matrix here, and have this covariance matrix is expectation x bar y and x bar y, and then this have expectation sorry, the covariance of x bar x bar, and this x bar y here, remember y is equal to mu1 x plus 1 mu2 x2 plus c, right? Or you can write it as a mu x mu transpose x times plus c. Then therefore, like we have here is basically expectation x times y transpose here, that is x transpose mu plus c transpose here, whatever, and xc is kind of independent of x, so this term can get zero out, only this left. Then I have sigma xx transpose times mu, basically. Oh, actually I don't need this transpose here. Anyway, all this covariance matrix is symmetric, it doesn't matter. So, and similarly, I have, like, let's say this is a sigma y is expectation of mu transpose x plus c times mu transpose x plus c transpose. Then if we expand that, basically only because c and x are independent, so we only have c times c have basically come out of n, this times this come out of this thing here. Then if we compute the determinant, what we can do is we can multiply this first row here by mu transpose, and then subtract the second row by this multiple. So therefore this I will get 0 here, and this I get mu transpose sigma xx mu plus n minus mu transpose sigma xx mu. So this got cancelled, only get n left. So therefore determinant is simply n times determinant sigma xx. So therefore, okay, this first term is easy. This thing here is actually just equal to n times n determinant sigma xx. So we find the one of the terms for the Wilson bound here. Now we're trying to look into the second term here, that hy given m1, m2. So now just look at hy given m1, m2. Because we have m1, m2, x hat is long, so we can add that in the condition. And then with x hat, we can subtract mu transpose x hat in the argument. And then because conditioning reduces entropy, if we remove this conditioning, we have a less than equal sign here. And then y is equal to mu transpose x plus c. So if we substitute that, we have this. And if we compute the variance of this guy, is actually just equal to this here. So because it's Gaussian, therefore it's just equal to 1/2 log 2 pi this thing here. And what we want here is actually a sum of all hy given m1, m2. So therefore, if we take an average of that, of hy m1, m2, by the way, this I remove this index here, but for each of this guy, basically, this this sigma w's hw in general, for at each time instance, the error can be different. So we have a sigma wi here, I have an index here. So just to indicate that, like, the noise, okay, it's not the noise, but it's like the error. Remember that we have w is actually equal to x minus x hat wi. So x has the same statistics everywhere, but x hat can be different. So does wi. So, but if we take an average of that, log here is because it's a concave function, then we can just use the Johnson's inequality. So instead of taking average of log, we can take log average of the argument, and average of the argument is actually the average distortion that we use sigma d to represent that, and the sigma d has to be less than or equal to the constraints s theta. Again, like these are matrices, like it's really like s. Writing it this way really means that like s theta minus sigma d is positive definite, semi-positive definite, or positive semi-definite. So let's see. And yes, we have that. Oh, by the way, like log is concave, and in terms of sigma, mu transpose sigma mu is actually mu transpose sigma mu plus n is a linear function. So therefore, concave of linear is concave. Here, I just want to show that that thing is linear. Okay, now let's look into the last term of okay, that we need to find the Wilson bound. Let's look at this guy here. So what we need to do to try to bound that guy is we are trying to construct another vector, or basically we call it y hat here, is a combination of x hat and also y, and we will use this to estimate x. So the estimation function we'll use is a linear estimation function that will basically, the estimate is equal to a times y hat. So you can see like each of this guy here is actually just sigma xy and sigma yy, sigma xy hat and sigma yy hat. So this is actually the average of sigma y hat over all time instance. And similarly for this guy also. So if we use such an estimate, then what we can claim is that, remember, we are interested in hxi given m1, m2, yn, and of course, if we want to bound that, we better find the covariance for this guy. And what we can claim is that the covariance of this guy will be bounded by the estimate that we have, because this covariance, this is basically the best estimate with the observation of m1, m2, and yn. But given yn, we know, what I want to say, given m1, m2, we will know x hat. And given x hat and yi, we will have y hat I, right? Or something like that. Or I should say, like, given m1, m2, I can know like xi hat. And then given xi hat and yi, of course this includes yi, this is just y1 up to yn, and we have some yi in the middle. And given yi and xi hat, then that's basically we have the yi hat. And this variance here is covariance here is basically the estimate with yi hat, right? So therefore, like, this is the best estimate with even more information. Then of course we have a smaller covariance. You can imagine in for scalar variable you have a smaller variance, and in vector case we will have a smaller covariance. So therefore we will have this equation here. So now the next thing we need to do is trying to bound this covariance of the estimate x tutor. Okay, sorry, actually I should say we have to bound the covariance of the error of the estimate x tutor here. Now to find the covariance of that estimate, or like the error of the estimate, we just expand that, like this is just equal to expectation xi minus a yi hat. And then if we expand the terms here, there's 4 terms here, and actually 3 of the terms are actually equal in magnitude, so 2 of them have the same sign, minus sign here. So therefore we actually have sigma x6 minus this guy here. And by the way, this is actually just a. Yeah. But for each of this average of the covariance, we will just denote this as like without the index simply. And now then we will compute each of these covariances. For the first one, let's say it's actually average of the covariance with that corresponding covariance with xi and yi hat, and this is just equal to expectation xi yi hat transpose, and yi hat transpose is actually just equal to yi xi hat. and yi is equal to mu. I should have transpose here, but actually yi is just a scalar. I can actually ignore this transpose. This is mu transpose x I times plus c I. So or like I can write xi transpose times mu I. Then if I take the expectation of this guy, then I have like sigma xi coming up here, and like for expectation of course ci is independent of that, then only have one term here for this part. It's a little bit ugly, maybe. And for expectation of xi and xi hat here, let's see, xi hat is, oh yes, because xi is xi hat plus wi, right? But xi hat and wi are independent, so therefore I have this expectation xi hat plus wi times xi hat is just equal expectation xi hat, and this is actually just equal to expectation, the covariance of xi minus covariance wi, because like x, or like the other way, actually we can write yeah, that's fine actually. So and similarly we can compute like covariance of y hat, and we have terms like that, and this is just simple algebra really. Now, okay, so we're coming back to this equation here. We have this guy and this guy, basically this one and this one computed like this, so we can substitute this into the equation here. So therefore we have the covariance of the estimation error is equal to this thing here, with the term substitute into that. Now what is interesting here is that like I can pull out sigma xx here outside and have this written as this multiplied by this, and this written as this multiplied by this. This is coming up to down here. I didn't write down, I just put two dots here. And we call the matrix inversion formula something that like if you have, actually I have another video on that. For the matrix inversion formula, if you have an A matrix plus some multiple of like 3 matrices, and this is a square matrix, this is a square matrix, then we can write the inverse of this sum here can be written like this. And what's interesting is that like this guy here is actually have a pretty similar form to this one. You have an A inverse here, A inverse here, A inverse here, and my A inverse in this case is sigma xx, right? Now, but this one here, and this is like my FAC, something like FAC here, FCA here, but the one center here, it better has a form similar to this way. So let's compute this guy here and see what is that. So if I compute FCA times FXX times FAC and write it out, I'll get something like that. and I compare this guy and this guy is actually pretty close. Like these off-diagonal terms are equivalent, and this just off by n, and this off by like sigma w minus this guy, something like. So therefore I can write this one here as this FCA sigma xx FAC plus this guy here. So now I can use the matrix inversion formula, and I can write this original form, like this thing here, this one here, that originally is in this form, into this form here. Then I have, this is basically A, and this is C, FAC, and so on.